So everyone, for the objective of this lecture, we have the first one is theory of pure bending, assumptions and relation, and second objective, why we estimate the product of inertia, and the third objective, we are going to talk about Mohr circle of inertia and how can we use it to get the maximum and minimum values of moment of inertia. First, we have some assumptions when there is a beam acted upon by pure bending. It's going to be deformed, but first let us examine the beam before deformation. We have two axes, X and Y, and we consider the section of the beam as rectangular section. In the first stage before deformation, we have vertical section perpendicular to the neutral axis, and in our assumption that the plane section perpendicular to the neutral axis before deformation remains perpendicular to the neutral axis after deformation. After deformation, the beam will take the form of the curved shape, and the perpendicular to that, it will not remain anymore as vertical, but will be considered perpendicular. The section will remain perpendicular to the neutral axis after deformation. Second assumption, the deformation due to the bending is small. Third assumption, the beam is initially straight, and all the longitudinal filaments bend in a circular arcs with a common center of curvature. This is mean all these perpendicular sections in this section, and if you assume there is another section, there would be plane section perpendicular to the neutral axis, and the third portion there will be another section perpendicular to the neutral axis. All these sections, if you are going to extend, they will meet at a common point and the line constituted will be a form of circular arc. Number 4, the deformation of the vertical in the vertical direction, i.e. in transverse strain, sigma yy may be neglected in driving an expression of the longitudinal strain. When we have a bending moment, there will be extension in the lower chord accompanied by compression in the upper chord. For the extension, always in the longitudinal direction, there will be a compression or transverse strain. This transverse strain in our case will be represented by the h over h, and it will be negative, while the longitudinal deformation will be the extension of length divided by the original length. Extension of length will be represented by the L over L, which will be positive. In sigma yy, we consider it has a small value and it will be deleted. Number 5, the radius of curvature is larger as compared to the dimension of the cross section. Number 6, the value of the Young's modulus of elasticity in both tension and compression will be the same. Next step, we are going to talk about the pure bending. What is the pure bending? The pure bending, which it means that the beam is subjected to moments on both sides and they are both equals. The shear value will be 0. Why? The shear value will be 0. Why? Because this bending moment on the right hand side will produce couple. It is anti-clockwise, so the couple will be upward here, the shear here, and accompanied by downward shear force on the right hand side, while this moment will produce resisting couple anti-clockwise, so the shear force here will be downward and the other shear force here will be upward. So downward and upward opposite to each other, and both two supports will cancel each other. That's why the shear force will be equal to 0. While for the bending moment diagram, if we are going to draw, this is sagging. It will be positive in value. It will go to the right support and will be closed here. So this from left to right, it will be subjected to bending moment of equal value, positive bending moment. For the left-hand side moment and the right-hand side moment, they will cause the beam to bend in a form of arc, and the enclosed angle will be alpha, as we can see in the diagram. The second case, when we have a pure bending, we have pure bending in case of you have a simply supported beam, hinged and simply supported beam, acted upon by two shear forces B and B of equal values, and they are acting on the third of the beam, L over 3, L over 3, and L over 3. In that regard, we'll have shear force diagram. We have here B, positive shear force coming up and go down until coming to B. And from the right-hand side, we have negative shear. It will continue until point D and closing. While for the bending moment diagram, as you can see, we have B multiplied by L over 3, SPL over 3, and BL over 3. This is the positive bending moment which we have. So for the section, the intermediate section, it will be having bending moment while shear force between C and D equal to 0. This is the second case of pure bending moment. The assumption number 3, that beam is initially straight. If we can see, there is a rectangular section, and this is a x and y x. And before deformation, if we take section apart distance by dx, and there is an element, small element, apart by distance y before deformation, and let us have a look after deformation, we'll find that the beam will bend in this form, and the neutral axis, which was horizontal, becoming curved like that. And we can see here the xx and y and the perpendicular x z. If we assume that the arc radius will be r and there is an r, the enclosed arc angle will be considered as the alpha. Now we are going to equate, and we are going to find the strain value before deformation. There was no strain. After deformation, this segment with the length dx, its length will become r d alpha. For the element at y distance up, its length originally was dx, while after deformation, the length will become r minus y multiplied by d alpha. So the length for this red line equal to r minus y multiplied by d alpha, while originally the length here was dx. Dx, if we are going to compare it, actually it's becoming in the neutral axis, there is no change. So we can take dx as equal to r d alpha. The deformation is extension or compression. For this case, we are above the neutral axis, so the deformation will be becoming negative. We have r minus 1 multiplied by d alpha minus r d alpha will be r d alpha minus r d alpha will cancel each other, and we are left with minus y d alpha. And since the strain is a deformation over the original length, the deformation is minus y d alpha, and the original length was r d alpha. So we left with minus y over r, and since due to the Young modulus of elasticity equal to the stress over strain, so we have our strain equal to minus y over r. This is the strain. So the F equal to the strain multiplied by Young's modulus of elasticity. It means that F will be minus y over r multiplied by E. And since we have the assumption of 4, the assumption of 4 that the Young modulus of elasticity is the same for in case of tension and compression. We'll continue in the next topic, we are going to get the relation for the stress and how can we get the Ix value and why Ixy at the end it has to become 0. Thanks a lot and see you.